Hello everyone. Reactions of free radicals. Free radical part 7. In the last two parts, that is 5 and 6, there also we have discussed reactions of free radicals. So it is just a continuation. So we will first have a quick brush up. So three fates of radicals, which is nothing but reactions of free radicals. So here we have seen in the first video, that is part 5, that two radicals when combining with each other, we are getting spin paired molecule. Now, though it is exceptional, but still we have seen this type of example. So here if the two radicals are same type, as you can see in this case, so in that case you can call it dimerization. Now the second part type, which is the most common, that is this one, where we have one radical R dot which is reacting with spin paired molecule, because we have two electrons here, it is spin paired, and here this A, any of this atom in this bond AB, if it is combining with R dot, suppose A, we are getting a new spin paired molecule and we are getting a new radical also. Now this is the most common. So we are basically continuing reaction under this heading. Though there is one more type which is a single radical, it is fragmenting to a new radical which is pH dot and CO2. So this type of reactions mostly observed with expulsion of small stable molecules such as CO2, CO and nitrogen. So in this case we are seeing CO2. But we are continuing the reactions that are related to the second type, which is the most common. Now under this type, addition type we have finished in the last class. Okay. In today's class we will start with different types of substitution. So see, this is number 4 reactions, and this is substitution reaction, halogenation of alkane, where one hydrogen will be substituted by halogen atom. Now why it is so important industrially? Because here some functional group we are introducing in the alkane. In alkane there is no functional group, but by this reaction we can introduce it. So that is the industrial importance. Here you can see the overall reaction RH, which is any alkane, in presence of chlorine and H nu or light, we are getting this hydrogen substituted by Cl and HCl. So this is the overall net reaction. But if we consider the steps, we know there is first initiation, and chlorine, this bond, it is not a very strong bond, so we do not need any another reagent to start the process of generation of Cl dot. Okay, so it can do it, that is we can do it without any help of any other reagent, because Cl-Cl bond breaking, it is not very highly energy requiring process. Here we are getting 2 chlorine dot, and in the propagation step RH, this bond will be broken, and this H, now it is combining with this Cl, and we are getting a new radical which is basically carbon based radical R dot. Now this R dot is reacting with more chlorine molecule, and we are getting the final product which is the RCl. Now if one question is arising in your mind that why R dot is, it is not directly reacting with Cl dot and it is generating RCl, but that is it may happen, it is not that it cannot happen, it may happen, but the chance of formation of RCl by this reaction, that is R dot is interacting with chlorine, the chance of this reaction is more. Why? Because we have used chlorine as one of the reagent. Cl dot is also there, but mostly the concentration of chlorine is high, so that is why the final product RCl mostly we will get from the interaction of this R dot with chlorine molecule. Fine. It may be also with bromine, but I am showing the mechanism with chlorine. So typically this chain reaction, as you can see, for one chain reaction, the propagation step, that is a chain reaction, it can continue 10 to the power 6 steps. So you can understand how explosive the reaction can be. Okay, so we should do this reaction with proper care. Termination steps, as we know, it can include combination of any free radicals, because here we have different types of free radicals. Cl dot, we have R dot, so any of these two can combine with each other. But propagation step, that is this step, we are getting our desired product which is RCl, where our hydrogen of RH is replaced by this halogen atom chlorine. Now we will see Regio selectivity. First look at this reaction which is basically chlorination. So once we finish this, then we will also compare with bromination. So what we mean by Regio selectivity? In the previous reactions that you have seen, there is only one type of hydrogen. That is a general equation. But suppose we have this propane molecule. Now this hydrogen, if this is removed, we will be getting the radical like this. But if these terminal 6 hydrogens are there, if they are removed, then we will get another type of radical. Now the major product we are getting from this radical, which is 55%, and 45% is the other one. Though this selectivity is not very high, but why it is so? Because see, the stability of radical, if you simply consider that factor, then we will not be able to explain. Why? Because here this hydrogen, which is at this middle carbon, that is only one hydrogen. But terminal position 3, 3, total 6 hydrogens are there. So the chance of formation of the radical, that is this one, suppose this is A radical, this is B radical. So chance of formation of B radical, though it is not very stable, but the number of these radicals will be high because there are total 6 hydrogens that can be removed. Okay, so that is why this is another factor. So if we combine these two factors, one is stability of the free radical, another one is number. So number is high for this terminal hydrogen. So that is why when we combine both this effect, after all we are getting, though major product we are getting from the stable radical, which is A radical, but still it is 55-45. That is, the selectivity is not very high. So this is Regio selectivity. Now consider another alkane molecule. Now here these 3 hydrogens, as you can see, if it is removed, we will be getting the radical like this. Suppose this is B. Now this is primary, but this hydrogen if we remove, now we will be getting tertiary. Now tertiary is obviously more stable compared to B type. Okay, but remember here these terminal positions, if you consider, total 9 hydrogens are there, and this is only one hydrogen. So number also you have to consider, that is the second factor. So from number factor there will be formation, that is total 9 hydrogens can be removed. So the chance of formation of B radical, though it is not stable like A, but as number of hydrogens are high, so combining these two effects, ultimately see we are getting 63%. So though A radical is more stable than B, but still the major product we are getting from this B radical, right? Now come to the bromination. So same type of substrate we will take. So here also we have taken propane, same type of substrate. This is also same, so that you can compare with chlorination. Here it is 55%, 45%. But now look at this bromination. The selectivity is so high, 97.3. And if we consider the second substrate, now though there is total 9 type of that is primary hydrogens, but still the selectivity it is 99%, that is greater than 99%. So this compound will be the major product. Now why in bromination we are getting more Regio selectivity? If we want to know that, we have to consider the energetics. Now the equations that you are seeing, the halogen atoms, it is general. So it may be chlorine, it may be bromine. So same type of initiation, propagation steps are written, nothing new, that we have already seen in the first slide. But here if we consider whether the steps are endothermic or exothermic, now this is the case. So the initiation step, as we are breaking this bond, it is always endothermic, whether X is Cl or Br. But when it is propagation steps, for the first propagation step number 1, if X is Cl, then it is exothermic, but for bromine it is endothermic. And for the second step, it is whether X is Cl or Br, it is always exothermic. And termination, it is always exothermic because 2 radicals are combined. So in this case, that is the first step of propagation. This process being endothermic for bromine, it will be the slowest step, okay? And that is the reason the stability and structure of this carbon radical, when it is bromination reaction, that will matter, okay? It will also matter for chlorination, but in case of bromination, it will matter more. So see, the stability and structure of this carbon radical, that is this one, it is important in bromination compared to chlorination. And that will lead to the more Regio selectivity that we have seen in the previous slide in case of bromination. Now as it is more regioselective, we can utilize this factor in another reaction, which is allylic substitution of hydrogen by bromine. So this hydrogen, its position is allylic. You can also take any other compound like this. We just have to have some allylic hydrogen. And when that is substituted by bromine, we are calling it allylic substitution. So as we have seen that tertiary radicals are more stable than primary, so allylic radicals are even more stable than tertiary ones. So that is why we have taken this type of substrate where we can replace allylic hydrogen with bromine. Now if we consider the steps, it is just like the same mechanism, initiation, propagation. But why we are saying this once more? Because here we can have some competing reaction. And what is the competing reaction? The competing reaction is basically radical addition reaction, where this substrate, that is the same substrate, the final product you will get this one. Now why we are getting so? Why we are not getting our expected product this one? Because after the first step, not first step, suppose Br dot is added to this CC double bond and we are getting this C dot. Now this C dot, because of presence of very large amount of bromine in the medium, because we have started the reaction with bromine, right? Because of large presence of bromine, so this type of addition reaction we can get. So there will be competition between radical addition reaction, which is this one, and the actual reaction we are trying to do, which is basically radical substitution, or better you say radical abstraction, where this C dot, it is basically abstracting one bromine atom. So this is basically substitution. If you overall see the process, it is substitution. Hydrogen is substituted by bromine, but this is addition reaction. So radical addition reaction, it will be a competing reaction. So what to do? What is the solution? The solution is we have to keep the concentration of bromine that we are using as one of the reagent as low as possible, but that is difficult. So there is alternative way. We can use a reagent which is NBS, because if we do this reaction with NBS, concentration of bromine will be very low. But how that will happen? First of all, we have to know the structure of NBS. So this is the structure of NBS. Now look at the mechanism. In presence of light, or that is H nu, or heat, this NBr bond is broken and we are getting Br dot. So Br dot is already produced. Now this Br dot, as we have seen the same mechanism in the previous slide. But remember, before going to the next step, look at this one, this HBr which is produced as a byproduct. This HBr, it can react with NBS and it can produce bromine. So here, the source of bromine, when we are using NBS, besides producing Br dot radical, because see, in the first step NBS is producing Br dot radical, so its role is not just to produce Br dot, but it also generates low concentration of bromine. See how it is generating low concentration of bromine by this reaction. So here NBS is allowing only one bromine molecule to form for every molecule of HBr, which is clear from this equation. So as this bromine concentration is low, because we are not using directly bromine, so its concentration is low, so the competing reaction, that will not be very important in this case. So these two steps in propagation step, it is same as we have seen in the previous slide. But here we are not using directly bromine to avoid the side reaction or competing reaction, which is radical addition reaction. Fine. So that's all for this video. In the next video also, this substitution will be, that is radical substitution will be continued, where in this case we have seen H is replaced by halogen, but in the next videos we will also see that halogen can also be replaced by H, that is the reverse reaction. And also there will be substitution of OH or CO2H, so that will be in the next video. Thank you for listening.